This lesson is part 2 of section 2.1 on tangent lines and rates of change. Now our objective today is going to switch a little bit. We're going to actually apply what we learned yesterday with the slopes of tangent lines and secant lines. We're going to find the average rate of change on an interval. We will find the instantaneous rate of change at a specific point and solve application problems that use the slopes of secant and tangent lines. So yesterday you were introduced to the slope of a secant line through a function. Now we call that the difference quotient, but we also have two other ways of saying basically the same thing. We find the average rate of change of a function, and we use different notation written here. And we can also call that the average velocity if it's in context to a distance and time problem. Alright, so even though these have different notation, each one of these looks a little bit different than the next, but actually each and every single one of these is simply the slope of a secant line through a function. So let's say we have some function f of x here, and as you can see we have points a comma f of a and b comma f of b. Now if I draw a line through those 2 points, we call that a secant line, and we have the coordinates a f of a and b f of b. Now if we find the slope here, what we're looking at is the change in the y values over the change in the x values. In other words, that's f of b minus f of a over b minus a. So that leaves us with our average rate of change, which is simply the slope of the line that connects these points. Okay? In other words, the slope of the secant line. Now, we actually referred to that yesterday as the difference quotient, but as you can see, the notation is a little bit different. Instead of writing a comma f of a, I now have x comma f of x, and instead of b comma f of b, I have x comma f of x plus h. Oh, sorry, that's actually supposed to be an x plus h here as well. Sorry about that. Okay, now, as you can see, if I take the change in y over the change in x, I end up with that difference quotient here. We simplify that difference quotient so that the x's cancel and you're left with just this h in the denominator. But again, you're looking at the slope of the line that connects those points. So here's a more simplified version of that difference quotient right here. Again, we're finding the slope between 2 points, and then when we simplify it, we end up with just that h in the denominator. Now, to see how your average velocity is related to the difference quotient, which is also related to the average rate of change, I want you to think about if you were traveling and you were taking the speed of your car over a certain amount of time and traveling a certain amount of distance. So if you were to graph this function, okay, you might have it be a linear function if you were going a constant speed at all times, but most likely because you're going to be stopping or braking or speeding up, that function would look more like this. Now let's say I wanted to find the speed I was traveling by using this graph. So speed or velocity is simply distance over time. Now if I'm looking at the speed, I'm going over a period of 2 different points. So here I've got 2 points graphed. Well then really what I'm looking for is the change in the distance over the change in time. So if I do that, I'm really calculating, if we can see change in distance over change in time here, all that I'm actually doing is finding the slope of the line that would connect those 2 points. Again, this is what we call the secant line. So if we bring this back to our note sheet here, all of these different terms mean the same exact thing. It's the slope of a secant line that connects 2 points on the graph of a function. So in our first problem here, it asks us to find the average rate of change of a function over a certain interval. I could choose to use the difference quotient here, but I also want to practice making sure that we can use this notation as well. Remember, an average rate of change is simply the slope, okay, of a line that would connect the points where one endpoint is at 1 comma f of 1 and another point is at 4 comma f of 4. Okay, so let's find and evaluate f of 1 and f of 4. So f of 1 is 1 and f of 4 will be 2 if I just plug that right into that function here. So I have the coordinate 1 comma 1 and 4 comma 2. I'm not sure why this is not letting me erase. So again, the average rate of change is simply the slope of the line that connects those 2 points. So what I'm going to do actually is use this notation because I just want you guys to get comfortable with that. We would take f of 4 minus f of 1 over 4 minus 1. But really what we're doing is we're taking y minus y over x minus x. So in this case, we've already found f of 1 and f of 4, so let's just substitute that in. That's going to be 2 minus 1 over 4 minus 1. Again, we're just calculating slope. So the average rate of change here over this interval is 1/3. Now question 2 is a little bit more of an application problem. Here it says a car leaves a parking garage and after a half hour it was 20 miles from the parking garage. 2 hours later the car is 80 miles away. We want to find the average speed or velocity of the car over the time period of these 2 measurements. So here let's make sure that we understand that when they ask for the average speed or velocity of the car, what they're really referring to is the average rate of change. So we're simply going to find the slope of the line that connects 2 coordinates. Now in this case, because we're looking at velocity, we know that that's supposed to be the change in distance over the change in time. So we're finding the change in the distance with respect to the change in the time. Now, in this case, they give you some information here. They say after a half hour, the car is 20 miles from the parking garage. In other words, if you wanted to write this in function notation, it would say something like, actually, we'd use a position function, and usually that's the notation S here. So S of 1/2 is equal to 20. So in other words, at a half hour, we are 20 miles away. And our other coordinate here, careful when it says 2 hours later that you don't use S of 2, because it's really 2 hours later, meaning 2.5 hours have passed. And the car is now 80 miles away. So we're really looking at coordinates 1/2, 20, and 2.5, 80. Now, if we want to find the change in distance over the change in time, again, this is just the slope, so we're going to calculate the change in the y values here. So the change in the distance here is represented by 80 minus 20, while the change in the time is going to be 2.5 minus 1/2. All right, so we end up with 60 over 2, so we have 30, and this is going to be in miles per hour. Okay, this is the units here. We're in miles over hours, so this is going to be 30 miles per hour. Now, this velocity here, we're not saying that this is a constant velocity. The car did not travel 30 miles per hour the entire time. It's just on average, its velocity was 30 miles per hour. In fact, if you wanted to find a more accurate velocity, in other words, if you wanted to know what the car was traveling at, let's say, I don't know, an hour and a half after it left the parking garage, then we're going to have to do something a little bit different than just finding the average rate of change or the average velocity. Okay, now let's come back to the graph of our secant here, and in this case, because of the notation I'm using, this would represent the difference quotient if I were to find the slope between the points P and Q. Now, hopefully at this point, you're also realizing that this slope between those 2 points also represents what's called the average rate of change, or the average velocity, just depends on the notation that you're using. Now, yesterday we talked about how we can find the slope of a tangent line to the graph here at point P if we were to just move Q closer and closer and closer to P. So as we move point Q closer to P here, H will get closer to 0. So we say that the limit as H approaches 0 of our difference quotient will give us the slope of the tangent line here at point P. Now remember, any of this notation here can change, so let me try to summarize so far what we've seen. Okay, so far we've seen the slope of a secant line referred to 3 different ways. We can call it the average rate of change of a function. So here we're using notation with f of b and f of a. We can call it the difference quotient, and here I don't have it simplified, but this would be f of x plus h minus f of x over h, because those h's would, or I'm sorry, the x's would cancel. But as you can see, the graph here is still the slope of a secant line. And we also have this third way that we can refer to the slope of the secant, and that's the average velocity. So here instead I'm using a position function s sub t, and here you can see we're just finding the change in distance over the change in time. So as I mentioned before, if we move point Q here closer and closer and closer to P, that means H will be getting closer to 0. So if we find the limit as H approaches 0 of this difference quotient, what we'll find is that we'll get the slope of a tangent line to the graph here at point P. Now, if we do the same thing in the other graphs, so for example here, if I move point Q closer to P, that means B is now approaching A. So if I find the limit as B approaches A of this average rate of change, I find what's called the instantaneous rate of change. And if I come over here to this velocity graph, if I move Q closer to P, that means that I'm getting T1 closer and closer to T sub 0, okay? In other words, if I find the limit as T sub 1 approaches T sub 0, I will find something called the instantaneous velocity. All right, so here we go. This summarizes everything I was just explaining. So the slope of the tangent line can be referred to in 3 different ways. We can call it the instantaneous rate of change. Now what this is saying is as you move Q closer and closer to P, you will get the instantaneous rate of change as opposed to the average rate of change. So it's the instantaneous rate of change at point P. Now over to the right here, we can say that the slope of the tangent line to this particular graph here at point P, that's referred to as the instantaneous velocity if this graph here is the graph of a position function. In other words, let's say we're referring to it in the car example here. If I am plotting my distance with respect to time here, then at point P, this is at some time period where I'm traveling a certain speed. And to find that exact speed, I find the tangent line so that I can find the slope of that tangent. So that gives me the instantaneous velocity. In other words, it gives me the velocity that something is traveling at a specific instant in time. And then finally in the middle here, obviously, this is the limit of our difference quotient, so it shouldn't just say difference quotient because that's not really what it's called. It's the limit as h approaches 0 of our difference quotient. So that also gives us the slope of our tangent line. All right, so here we have a nice little summary that compares the slope of your secant to the slope of a tangent line. Now, when we're talking about the slope of a secant, we refer to that as the difference quotient, the average rate of change, or the average velocity, and it all just depends on the context of what you're looking at and what the graph looks like or what the question is asking. Now, when we talk about the slope of a tangent line, we're moving that point Q closer and closer to P so that we're finding really the limit as h approaches 0 of your difference quotient. We call that also the instantaneous rate of change or the instantaneous velocity. So you're finding a specific rate of change or velocity at a specific point. All right, so let's return back to our note sheet now. We're going to do a couple of practice problems. But as you can see, I've summarized all of the different forms of the slope of a tangent line. So if you notice all the way over to the right here, in parentheses I have the word instantaneous. And that's because sometimes books get a little bit lazy. Instead of saying the velocity, instead of saying the instantaneous velocity, they'll just refer to it as the velocity. So if they want the instantaneous velocity, sometimes they just say velocity. But if they actually want the average velocity, which would be in the slope of the secant, then they specify average. So if you don't see the word average, you're not finding an average, you're finding the instantaneous velocity. All right? All right, so let's begin with our first question here that asks us to find the instantaneous rate of change of this function. And you'll notice it's the same function I used on the front. But this time we're finding an instantaneous rate of change at a specific x value here, 4. Okay, so I don't want to throw like another set of notation on top of what we already see here, because I think that's a lot. But basically, if you wanted to refer to this using this instantaneous rate of change here, you don't have two different points. So instead, use f of x, and for f of a, use f of 4. Okay, so that's how you would find the instantaneous rate of change here at x equals 4. You have to find the limit, this time as x approaches a. So whenever you see that b here, we'd change that to f of x here and x minus a in the denominator there. But what I'm going to do, just because I think most of you are probably really comfortable now with using the difference quotient, I'm going to use the difference quotient to find this instantaneous rate of change. All right, so I want to find the limit as h approaches 0 of f of x plus h minus f of x over h. And just by substitution here, I'm finding the limit as h approaches 0 of root x plus h minus root x over h. Now, in this case, because I have those, this form up here, and I tried to just plug in 0, I'm going to get an indeterminate form. So what I'm going to do here is kind of manipulate this, and I'll multiply by root x plus h plus root x over root x plus h plus root x. All right, and this is a really similar strategy that we've used already, just multiplying by the conjugate here. So if I simplify, I have the limit as h approaches 0, and in the numerator, that'll be x plus h minus x. Now I'm putting it in parentheses. I know you don't really need the parentheses here because there's only one term, but make sure you get in the habit of doing that. Otherwise, you'll kind of mess yourself up when you don't distribute that negative. All right, so then I have in the denominator h times root x plus h plus root x. Now, obviously, those x's do cancel here. And the h's, I'll just write it out here. So I have h over h times root x plus h plus root x. So here, those will cancel out. And I'm left with 1 over root x plus h plus root x. So I want to find the limit as h approaches 0 of 1 over square root x plus h plus root x. Now to evaluate this limit, obviously you can just plug in h is 0 here because you don't end up with something undefined or the indeterminate form. You end up with 1 over the square root of x plus the square root of x, which is 1 over 2 root x. So this represents the slope of the tangent line for this function. Now, I want to find the instantaneous rate of change at x equals 4. So in other words, I want to find the slope of the tangent at specifically x equals 4. So all I have to do is plug in 4 into that function. So to answer this, I do 1 over 2 times root 4. So I get 1/4. So this is the instantaneous rate of change at x equals 4. All right, so I realize that that's quite a bit of work here, and actually it's very similar to what we've already done in yesterday's, lesson. So that's why technically you could do these problems without having to watch this particular lesson, but I do want to show you a method that you can use that will simplify all the work that you just had to do. So instead, I'm going to use this notation here to find the instantaneous rate of change. All right, so if I want to find the instantaneous rate of change, I can use this alternate form. I can find the limit as x approaches 4 of f of x minus f of 4 over x minus 4. So just by substitution here, I'll have the limit as x approaches 4 of the square root of x minus the square root of 4 over x minus 4. So I end up with the square root of x minus 2 over x minus 4. Now I know some of you mentioned that you like to multiply by the conjugate, and some of you I think like to factor. I'm going to factor here instead of multiplying by the conjugate. Because I see this x minus 4 in the denominator, I can say that this is equivalent to root x minus 2 in the numerator, and then root x plus 2 times root x minus 2 in the denominator, because if I multiply those both, I'd get this difference of squares, x minus 4, even though that doesn't really look like a square. I can make it a square if I call one of those terms root x. All right, obviously these terms will now cancel, so I'm left with 1 over the square root of x plus 2. Now, because I'm finding this limit as x approaches 4, I'm going to evaluate this limit. Okay, so the limit as x approaches 4 of 1 over root x plus 2. So we plug in 4 here, and we have the limit, well, let's just write it over here. The limit will equal 1 over the square root of 4 plus 2, which is 1/4. So we get the exact same result that we did when we used the difference quotient. It's just a little bit faster here. Okay, the last question of the lesson says the height of a paper airplane in meters can be modeled by the position function given here, where s is the airplane's height at time t, which is in seconds. We want to find the position of the plane at time is 2. So this question is pretty rudimentary. To find the position of the plane at time is 2, all we're really evaluating is s of 2. So we're just plugging in 2 into the function. So obviously that's pretty standard stuff. The reason why I'm putting that question right before we find the velocity is because I want you to know that there is a big difference between finding the position of this paper airplane as opposed to the velocity of that plane. So remember, when it says find the velocity, they're really asking for the instantaneous velocity. Instantaneous. Okay, so we're finding it at 3 different points. So we're going to have 3 different answers, whereas the position of this plane at time is 2 is only one output. In this case, what is this? 4 times 9, 8, so we have 28. So this is 28 meters. Okay. Now for part A, they ask us to find the instantaneous velocity of this plane when time is equal to a seconds. So rather than giving you a specific time, they're just giving you an arbitrary time value. So I'm going to use the notation in the top right corner of your node sheet, but instead of using s of t sub 1 and s of t sub 0, I'm going to just use s of t and s of a. Okay, so we're finding the limit as t approaches a of s of t minus s of a over t minus a. Now I want to note that you could just as easily find this answer here, the instantaneous velocity, by using the difference quotient, and you're probably comfortable with using the difference quotient since you've done it already a few times. So you're more than welcome to continue to use that here, but I'm just going to use a little bit different notations just so you're seeing and being exposed to other forms of this notation. So anyhow, now I have to make some substitutions, okay, into here. So I have the limit as t approaches a of s sub t is negative 2t squared plus 36, and then s of a, so I have to subtract this, will be negative 2a squared plus 36. This is all over t minus a. So as you can see, if I distribute that negative here, the 36 is going to cancel, and I'm going to be left with the limit as t approaches a of negative 2t squared plus 2a squared over t minus a. Now I'm going to factor out a negative 2 from that numerator here. So I have t squared minus a squared over t minus a, and then I notice that this is a difference of squares, so if I factor that even further, I have t minus a times t plus a in that numerator, and that t minus a will cancel with that denominator. So I want to find the limit as t approaches a of negative 2 times t plus a. Okay, and again, if we want to evaluate a limit, remember you just plug in this value here. So I'm going to plug that in for t here, and I end up with negative 2 times a plus a. This is negative 2 times 2a, or just negative 4a. So the instantaneous velocity of the plane at time is equal to a seconds is going to be given by negative 4a. So this is for any arbitrary value of time. Now this is also representing the slope of the tangent line to the curve here at a seconds. Also, I want to mention the units here. I forgot to do that real quick. So the units are going to be in meters per second. Okay. Now this negative sign out in front just indicates a negative direction of motion. In other words, the plane here would be falling. It doesn't mean that you have a negative speed or negative velocity. It just means that you have a negative direction of motion. Now, in part B here, we're asked to find the instantaneous velocity of the plane when time is equal to 2 seconds. And because we've already done this work here of finding the instantaneous velocity at any arbitrary value of time, all I have to do is make a substitution here. So I'm just going to plug in 2 into negative 4a. So if I evaluate here with a equal to 2, then I have negative 4 times 2. That gives me negative 8, and again, this is meters per second, okay? Now what this answer is telling me is that at that instantaneous moment, at time is equal to 2, the plane is traveling at negative 8 meters per second. And again, this negative just means that it's falling, okay? It just indicates a direction. Now in part C, they ask us to find the velocity of the airplane the instant that it strikes the ground. So in other words, when it hits the ground, it's going to have a height of 0. So in that position function, s of t, we're setting that equal to 0. In other words, negative 2t squared plus 36 will equal 0, and we're going to solve for t. So we want to find out the exact moment in time where that airplane will strike the ground. Once we find t, then we know how to find the slope, okay, at that specific value of time. So if we solve here, we end up with t squared equaling 18. So t is going to equal positive or negative root 18, but obviously time should always be positive. So we're going to take the square root of 18, which is going to be 3 root 2. All right. Now, what we're going to do is plug in this time period, right? That just like it's basically exactly the same as question B. It's just that we had to find the time on our own. So now we're just going to plug in 3 root 2 into that negative 4a. So we're letting a equal 3 root 2. So we have negative 12 root 2, and this is in meters per second. Okay. So this is the exact velocity, the instantaneous velocity, the moment that that airplane will hit the ground. All right, so that is the end of the lesson. I know there's a lot of vocabulary in this particular section. Just make sure that you understand the difference between the slope of a tangent and the slope of a secant, as well as the applications of those different slopes. Nice job. I will see you guys in class tomorrow.